Metal casting covers a wide range of processes. For this very large ferrous casting, the most appropriate method is the pit moulding technique. For metals that melt at temperatures greater than 1000 Celsius, for particularly intricate or complex shapes, and for materials that are difficult to machine, investment casting could be the best choice. When only a few hundred units are required, moulds made by the cold box or green sand method would be appropriate. In mass production situations, particularly where aluminium, zinc, magnesium and brass are to be cast, a die casting process may be the most effective way of making quality castings at minimum cost. Gravity die casting, also called permanent mould casting, is used to produce castings in medium quantities, castings requiring maximum internal integrity, or castings that require heat treatment. The process is also used for very large numbers of castings that have complex internal shapes requiring the use of cores. The main parts of the die are risers, down sprue, die block and its movable parts, ingates and dross trap. In this casting, sand cores are set into the die. Molten metal is poured into the pouring basin, enters the runner system, fills the die, cools and solidifies. The die opens and the now solid casting is removed. Cores are added and the die closes, ready for the cycle to recommence. The cores can produce a simple hole in a casting or a complex cavity. They are made from a bonded sand, and a new set of cores is required for every casting produced. The most commonly used alloy in gravity die casting is the aluminium silicon magnesium alloy, as it has good castability and good mechanical properties. The metal generally takes 1 to 4 minutes to solidify. These risers feed the casting with molten metal. Ceramic die coats are sprayed onto the die, and these will help control the rate of heat transfer within the die. Components suitable for gravity die casting will generally have wall thicknesses greater than 3 millimeters, and commonly weigh between 200 grams and 10 kilograms, although much larger castings are possible. Gravity die castings have a medium surface definition that can be better than sand casting, but not as good as high-pressure die casting. All of the runner system is cut off and remelted, being combined with 70% new metal. There is no waste with gravity die casting. An important modification to gravity die casting is tilt casting. Molten metal is loaded into a trough called a launder. The die is gently tilted back, causing the metal to flow smoothly out of the launder and into the die. With tilt casting, the runners and risers can often be kept small. In this case, only 20 to 30% of the metal cast needs to be recycled. After 3 minutes, the aluminium alloy has solidified. The die opens and the casting is removed. This process is ideal for large castings where smooth filling produces castings of high integrity and good surface finish. As there is no splashing, there is a reduction in the amount of oxidation of the liquid metal and the entrapment of air bubbles in the finished casting. Another advantage of the process is that fettling, the removal of the fins and runner system, is generally kept to a minimum. The main disadvantage of tilt casting is the higher initial cost of the tilt casting machine, and not all casting shapes lend themselves to being filled by this method. But where high integrity castings are required, tilt casting should be considered. In the automotive industry, large numbers of cast aluminium manifolds are required. To produce these, the tilt casting process has been largely automated by putting 12 casting machines on a carousel. The 700 kilogram capacity dosing furnace delivers an exact quantity of aluminium alloy into the launder. The die tilts back as it moves around. When the metal has solidified, the die tilts forward and opens, allowing the casting to be removed. On this carousel, 2 different manifolds are being made at the same time. The manifold is given an identification stamp and is put on a conveyor system to slowly cool for 2 hours, after which any fin formed where the die parts join is cut off and the runners and risers are sawn off. There's only a 3% scrap rate for these castings, the scrap being returned to the furnace. This defective casting shows the thin 3.5mm wall and the very complex internal shape of the manifold, which makes it difficult to cast. The cores to produce this internal cavity are loaded onto the die. The die closes and the process recommences. The production of these cores is an art in itself. They are produced by the heated core box method. This machine produces 3 core parts at a time. A fine sand containing 2 to 3% thermosetting resin is used. It sets when it comes in contact with a hot core box. The die closes and the dump box and core box are tipped over, thus making the next set of parts. All parts of the core are carefully checked, as a defective casting is an expensive item. A coat is sprayed on to help produce a correct cooling and solidification condition in the die and to enhance the surface finish of the casting. Glue is applied so that the whole assembly is joined together. It is difficult to produce a casting with a wall thickness of only 3.5mm. A small misalignment of any part of the core will lead to a defective casting. It is inspected and all the gaps are filled, as any indentation in the core becomes a fin in the final casting. To produce a complex cavity in a casting requires a lot of work by many people, and the margin for error is very small. Low-pressure die casting is generally used for producing large aluminium alloy components where very smooth filling of the die is required. This process produces high-integrity castings that can be heat-treated, and like gravity die casting, sand cores can be used for complex detail. The low-pressure die casting machine is made up of a die, a riser tube, a crucible that can hold 700 kilograms of molten metal, a pressurizing system, and a heater to maintain the metal at an exact temperature. When low air pressure of several hundred kilopascals is applied, the metal is forced up the tube, gently fills the die and solidifies. The pressure is then released, and the liquid metal in the riser tube returns to the crucible. After about 40 castings have been produced, a hatch in the base of the low-pressure die casting machine is opened and the crucible is refilled. The process then recommences. These are cylinder heads that are being produced for the export market, and they must be defect-free. They require a complicated set of cores to produce all the internal waterways, inlet and exhaust ports found in a modern cylinder head. Thousands of these cylinder heads are required. It is for these reasons that low-pressure die casting is the logical choice. Wire mesh strainers are added to ensure that only clean metal enters the die. The die cavities have been sprayed with a ceramic die coat during initial die preparation to help maintain correct thermal gradients across the die and ensure a defect-free solidification. The die is closed and air pressure of 300 kilopascals is applied. Temperatures and pressures are carefully controlled and monitored to ensure casting quality. The air pressure is released when the metal has solidified in the top of the riser tube. Later the die opens and another casting is produced. The low-pressure die casting process gives a very high yield as the amount of metal used in the running system is quite small. Following visual inspection, the cylinder heads are allowed to cool slowly. After having their runner systems cut off, they are loaded into baskets for heat treatment. For this application, a heat-treatable aluminium silicon copper alloy is being used. To improve the strength of the cylinder heads, they are heated to 510 Celsius and soaked for 8 hours. They are then promptly quenched in water and reheated to 160 Celsius for 3 hours. This heat treatment greatly improves their mechanical properties. To ensure that all castings are 100% gas-tight, they are impregnated with a polyester resin that will seal any minor defects that might be present. Cold chamber high-pressure die casting is generally associated with the aluminium alloys, but increasingly with the magnesium alloys. Under high pressure, molten metal is sprayed into the die cavity so as to produce finished components requiring little machining. The cold chamber die casting machine consists of a plunger, a cylinder called a cold chamber, and a die that is split into halves. The moving half has ejector pins that push the casting off the die cavity. Molten metal is poured into the chamber. The plunger forces the metal into the die at pressures of 100 megapascals or more. This gives rise to a very strong outer skin on the casting. The die cavity is sprayed with a water-based lubricant that cools the die and helps extend die life. Cold chamber high-pressure die castings can maintain high dimensional tolerances and excellent surface detail, but generally are not weldable or heat treatable. These transmission housings are required in very large quantities, and the casting process starts with new aluminium alloy that is combined with 30% recycled material from within the plant. This is melted in a reverberative furnace. This alloy combines good strength with excellent fluidity, an important factor in successful cold chamber die casting. The alloy is degassed. If the gases are not removed at this stage, they will come out of solution during solidification of the metal, causing porosity in the casting. A sieve is used to finally clean the molten metal as it is poured into the dosing furnace. This furnace feeds the molten metal into the cold chamber of the machine. The die opens and an actuated arm removes the casting from the die. The die cavity and metal cores are drenched with a water-based die spray to selectively cool and lubricate parts of the die and help extend die life to 150,000 shots or more. This machine has a clamping force of 2,250 tonne, and the machine's cycle time is 90 seconds. The cost of a machine of this size is $4.5 million, a large investment that must be repaid with high productivity. This gearbox casting is 100% pressure tested for soundness. and 1 in every 100 is checked radiographically for any internal defects that might have arisen during casting. A die set to produce this casting has a cost in the order of $500,000. This means that each shot costs $2 to $3 in die wear alone. Other materials used for high-pressure cold chamber die casting are the magnesium alloys and the brasses. Magnesium as small particles will burn in the air, so when used in conjunction with a high-pressure cold chamber die casting machine, it is necessary to use a mixture of gases that do not support combustion and are heavier than air to form a blanket which protects the molten metal in the furnace. The main advantages of the magnesium alloys are their high strength and stiffness to weight ratio. Mobile phones must be lightweight, strong and able to shield electromagnetic radiation. For these reasons, a magnesium alloy was selected as the material for their chassis. A sealed siphon delivers the molten magnesium alloy into the cold chamber. The piston forces the metal into the die. It solidifies and is pushed off by the ejector pins. 6 components are made with every shot. With a wall thickness of only 0.4 of a millimetre, the casting is checked against a strong light for any defects. The extensive flashing is partially due to the high fluidity of the magnesium alloys. Australia is a world leader in pressure die casting technology. One of the main reasons for this is the research work carried out by the CSIRO over the past 25 years. A computer software package called CastFlow has been produced to assist the designer to quickly develop a unique tapered tangential runner and gating system that matches the metal pumping capacity of the pressure die casting machine. It will allow a runner and gating system to be designed and optimized within a few hours. With this technology, die trial and error can be kept to an absolute minimum. The arrows are the gate velocity vectors, and they verify that the metal flow out of the gate and into the die is correct. Another software package is CastTherm, which predicts the thermal distribution throughout the die. It displays the temperature gradients in any section taken through the die block. Most importantly, this allows the correct placement of heating and cooling circuits within the die block, and to a lesser extent, the correct quantities and placement of coolant that are sprayed onto the dies. A third software package is CastPulse, developed by Dr. Ho Xiao. It monitors the operation of a die casting machine in the finest detail. It reveals metal pressures, gate speed along with hydraulic pressures and piston speed. With this information, the machine's operation can be optimized or monitored for any deviation from correct operation. It is this technology that can give the edge when competing on the world market. These aluminium heater units are die-cast, with their heating elements included as part of the final casting. This is called an insert. The dies are cooled. The heating element is clipped into place, so that as the die fills, the molten metal flows around the element, causing it to become an integral part of the casting. The castings are cooled in a water spray and contract, so that when they are trimmed to the correct size. All the offcuts are remelted and reused. These iron laminates are part of a rotor in an electric motor. The stack of laminates is inserted into the die cavity. The pure aluminium flows around the laminates and mechanically locks them together. As well as this, the aluminium acts as an electrical conductor and also provides the cooling fan fins for the motor. The rotors have been machined and are now assembled into the die-cast aluminium pump body. These castings have required only light machining where the bearings are to be located. The external finish has been obtained by powder coating. The hot chamber die casting process is generally confined to the low melting point zinc alloys, although some magnesium alloys can also be cast by this process. The die casting machine contains a heated bath of molten zinc alloy, in which is immersed a cylinder and plunger. A gooseneck connects the bottom of the cylinder to the die. The plunger pushes the molten zinc up the gooseneck, where it is sprayed into the die cavity and solidifies as a casting. The die faces are sprayed with a lubricant, which extends die life and helps the casting to be released. The die closes and the cycle recommences. The process runs automatically, such that one operator can look after many machines. As the zinc alloy melts at less than 410 Celsius, the fuel costs are less per unit produced, die life is longer, at least 500,000 units from one die set, and the cycle times are much faster than any other casting process for a similar size component. Hot chamber die casting can produce castings having wall thicknesses as thin as 0.25 of a millimetre and products with very fine surface detail. The die is in two parts, a moving part that contains the sprue post and the fixed part with the sprue bush and runner system that feeds the metal into the die cavity. It will also contain any moving die segments. The casting is removed from the cavity by the sprue post and is flicked off by the ejector pins. A well-designed die casting generally replaces a number of parts made by other processes, in this case from 2 to 1. One of the advantages of the hot chamber die casting machine is that the zinc alloy ingots are melted within the machine itself, eliminating the need for external furnaces and ladling, thereby simplifying the plant layout. The process is a natural for the production of very large numbers of small components using a zinc alloy. In the case of these hose fittings, the runner system is sheared off and the internal thread is tapped in the 1 setting. The parts are dipped into a sodium dichromate solution. This process is called chromate passivation and is an inexpensive method of improving the corrosion resistance of the zinc die castings. By using a zinc die casting, this lock body has been able to combine bosses, guideways, nuts, pins and variations in thickness, all in the one component, leading to a great simplification of manufacture. This gear shift knob is made by the combining of a plastic moulding for texture and looks over a zinc die cast body for increased mass and just the right feel. Zinc die castings can be easily electroplated. For chrome plating, first a layer of copper is applied, then a layer of nickel, and finally a lustrous layer of chrome. There are many other plating processes that can be readily used with zinc die castings. They can also be painted or powder coated. With hot chamber die casting, the surface finish and design features of a casting are only limited by the designer's imagination. Squeeze casting produces high-density, defect-free components, having excellent surface detail together with holding close tolerances. The castings can be heat-treated, welded or plated. The machine is made up of a die set in which the ingate is considerably larger than that used in a conventional pressure die casting machine. A shot sleeve and piston moves between the die and the ladle. The shot sleeve is filled with molten metal. Swung under the die set, the piston moves up so that the die slowly fills from below with molten metal with minimum turbulence, no splashing and no entrapped air. The pressure is maintained during solidification, such that the process is akin to extrusion or forging. The close contact of the metal to the die increases cooling rates and reduces cycle time. However, die life is also reduced. These disc caliper components are required to have very high integrity to be able to be heat treated, have fine surface detail and close dimensional tolerances. In this situation, squeeze casting is an appropriate method of manufacture. With modern manufacturing, it is essential to match the most appropriate die casting method to the product design and material selected to produce quality products at a minimum cost.